It is my distinct honor and privilege to welcome Professor of Physics and Senior Data Science Fellow at Belmont University, which is in Nashville, Tennessee, Dr. Scott Hawley, who I first met almost 6 years ago when we were both participants in a program sponsored by Scholarship and Christianity in Oxford on science and questions in science and religion. When Aisha and I settled on this particular topic this year, I said, I know a guy. We contacted Scott and he was excited to come join us this morning. Dr. Hawley teaches physics courses for audio engineering students as well as deep learning and AI ethics. He also teaches an interdisciplinary honors course on classification methods throughout history. As a postdoctoral researcher at the Albert Einstein Institute in Germany and at the University of Texas at Austin, he helped perform supercomputer simulators of gravitational wave detectors, the most sensitive instruments devised by humankind. I'm going to trust him on that because I am a biologist. So this is wonderful. In the early 2010s, his teaching of audio engineering students led him to divert his research goals toward machine learning methods for signal processing. His publications have appeared in journals such as Science, like the one word science, the Astrophysical Journal, Classical and Quantum Gravity, Perspectives on Science and the Christian Faith, and the journals of the Acoustical Society of America and the Audio Engineering Society. His recent work with generative AI unicorn startup Stability AI resulted in the stable audio system for high-quality text-to-music synthesis. In other words, he knows what he's talking about. Thanks for joining us this morning. Please welcome Dr. Scott Hawley.
Hey, everybody. Good morning. I'm going to move this thing over this way to where I can see my slides, because I know you can see my slides, but if I have that podium in the way, that's going to be like this. Yeah, all right. So I got two different talks for y'all today. I call them, in broad strokes, sort of detectors and generators. We were trying to think of what would be good and useful to a lot of people. And this is one of these slides where I thought it might be cool to animate one little thing at a time, but this isn't going to work. So unless we have a clicker. Do we have a clicker? We'll just do this. Here we go. Okay, so I'm going to be sharing metaphors in faith and science that are meaningful to me. So if you come for apologetics talks, that's fine and that's good, but that's not going to be today. We can do that afterwards. So these are going to be reflections, kind of devotional analogies that are meaningful to me, and that my hope is that some of them would be meaningful to you. It is true that a lot of times things in the Bible are shared in the form of metaphors, things about farming, oxen, and so forth. At some point, Paul even says, is it really about oxen that God is concerned? Was he not speaking to us? And I notice if, to the extent that there still exist Christian bookstores, at least in terms of the book market, sports analogies and business analogies for the Christian faith, for understanding devotion abound, but scientists, we're believers too. We have our own perspectives. We have our own things that resonate with us. And we have some perspectives that I think can be helpful, or at least, if not helpful to the wider population, at least meaningful to us. I'm also going to claim on a somewhat philosophical level that science itself is a series of metaphors. We can go deeper into that if you want. My field, I came to Belmont because I was a musician who wanted a day job, so I could teach physics with a PhD, and then I got into machine learning when I saw that it was going to really affect my students' lives. These are going to be personal reflections. I'm definitely going to draw a lot of analogies with Scripture and mention Scripture, but just the caveat to say, take the good from this that you can, and if something doesn't resonate, we're going to talk about resonance. If it doesn't resonate with you, then go on with it. But yeah, this has about as much weight as I included golf, sports ball, birding, fashion, cake baking, Baldur's Gate 3, or differential geometry. If any of those resonate with you, you should give a talk at some point. Okay, these two talks, so one is going to be before lunch, and we're going to jump into, this is the pre-talk, all right? This is the startup talk. I'm going to divide them into two major kind of categories that we often see with machine learning or AI, or at least as they go nowadays. And one is the discriminative side, the detectors, the classifiers, the things that generate decisions for things, that categorize. And we see, I'll throw in some other biblical examples as we go forth, but there's something about observation and recognizing things that appears in Scripture and in, for example, Jesus' words. And there's a lot to do on the physical side and on the AI side with things like filters and damping and similarity metrics. And then after lunch, we're going to talk about the generative side of things, both on a human level and on the AI level. So generative AI is this buzzword that people have been going nuts about for a while, and I was privileged enough to be put up to one of the big startups for that. And so dominant paradigm, for a lot of things, neural networks works really well. If you don't know what those are, that's okay. Don't worry about it. I'm just saying I'm not going to be talking about there's a whole lot that we could talk about today. And I'm going to try to limit it and focus it in certain areas. But definitely, here's an example of the way that my work sort of rewrites sometimes when I'm reading the Bible. When Paul says, be not conformed to the patterns of this world, but be transformed through the renewing of your mind. Throughout history, right, we've had different analogies for understanding the human being or understanding the universe. For a while, there was this idea like the universe is like a clock, and then computers came along and said, oh, the mind is like the computer. Oh, actually, the universe is like a computer, right? For me, one of the dominant metaphors, the sort of hammer that I end up finding nails for is neural network. And so when we're talking about being renewed in our minds, it is very true that by changing the weights, the connections in a neural network, whether a human neural network in the brain or a computerized artificial neural network, you can get the system to do very different things. Also, I'm just going to throw out a few books that I like, that I think are good. So y'all are probably familiar with John Polkinghorne. So he has this book, The Faith of a Physicist. And yeah, today is going to be a little bit of an insight into the faith of this physicist. And also, Tom Newberry's kind of daily guide, 40 Days to a Joy-Filled Life. He's got a lot in there about filters and detectors, and both focusing on things and ignoring things. And one of his aspects of going towards a joy-filled life is learning to filter out a lot of things. So, throw that in there. Yeah? All right, so part one is detectors, or the title that I supplied was Eyes That See, Ears That Hear, Detection, Filtering, and Classifying by Humans and Machines. And yeah, that's my electronic address. So there are so many places that we could pick in the Bible, and I'm not confident that this is the absolute best, but this is something to get us started as we're talking. So this is from Ephesians 4. Paul saying, look, I tell you this, I insist on it in the Lord, that you must no longer live as the Gentiles do in the futility of their thinking. They're darkened in their understanding. This is a pick-me-up verse for everyone. They're darkened in their understanding, separated from the life of God, because the ignorance is due to the hardening of their hearts. We'll get to that in a little bit. Having lost all. So I'm highlighting certain words. Sensitivity. We're going to talk about sensitivity. They've given themselves over to sensuality, so as to indulge in every kind of impurity. They're full of greed. That, however, is not the way of life. You learned when you heard about Christ and were taught in Him, in accordance with the truth that is in Jesus, you were taught, with regard to your former way of life, to put off your old self, which is being corrupted by its deceitful desires, and to be, once again, made new in the attitude of your minds, and to put on the new self, created to be like God in true righteousness and holiness. That's going to be one aspect to get us started. I'm going to throw out a few more that will color before I'm going to jump into science pretty hardcore in a little bit, okay? But these are some of the things that are on my mind. The phrase, whoever has ears, let them hear. This appears throughout the New Testament. Depending on the translation you use, NIV, it's 15 times. From the Gospels all the way through to Revelation. Jeremiah talks about how people have eyes and don't see, or they have ears and they're not hearing. And we see this as well. Sometimes people can have the sensory apparatus to detect something, and yet they're not detecting it, they're not recognizing it. So it even appears as early as Deuteronomy, where all these amazing miracles and things happened as God was leading the Hebrews through Egypt and in the wilderness. And so it says, with your own eyes you saw these great trials, those signs and great wonders. But to this day, the Lord has not given you a mind that understands, eyes that see, or ears that hear. So again, we're going to focus on, and this can happen a lot with human and neural network systems. In order to detect things, there needs to be some training. And one other one here we have, Hebrews is saying, solid. I'm taking this a bit out of context. The writer's telling these churches, you should be a little further along than you are right now, but you don't get solid food, you need milk, because solid food is for the mature who by constant use have trained themselves. So this notion of training appears a lot in machine learning as well, to distinguish something, to distinguish good from evil. So these are going to inform a little bit of some of the science that we're going to talk about, and when I'm doing the science, or back and forth, my brain is drawing these connections unbidden, essentially. Okay, so we're going to talk about detection. We're also going to include with all that, I'm going to throw in, even though some people may say these are slightly different. Identification, classification, recognition. I like to throw in the memes when I can. So this kind of stuff, it's fundamental to being human. Joy mentioned that I teach an honors class on, it's called Aristotle to Algorithms Classification throughout history, and it really is just part of what we do. Yeah, so detection is just realizing that something's there, something. What kind of something, maybe we don't know yet, but then figuring out, hey, what is this? What is this thing that's out there? This appears in pretty much every field known to man. I mentioned medicine and law. It certainly appears in physics. It appears in biology. And a lot of times, the way that we do this is through some kind of measure of similarity to what is expected. And we'll get into that as we go. So now, I'm just going to throw this in there. As a physicist, I've pretty much usually been interested in what we call regression, fitting curves to things. And this matter of identifying things and categorizing things, that's for biologists, that's for other scientists and maybe astronomers, the closest thing. And as I was getting into machine learning, I found that everybody was interested in these sort of what I'm calling classification problems, which also includes detection and identification. And I was just confused, like, why is this such a big deal to everybody? That's not even real science. Science is fitting curves to things. I'm joking a little bit, but that's how I grew up as a scientist. It's because a lot of things that happen in the sphere of human life involve making decisions about things and putting things into categories. And these are typically discrete. Our governments are all based on making decisions about things. And so this appears, I give a few examples: loan detection, object detection, criminal risk assessment. There's a lot of money to be made. I'm a fan, I don't know if you ever saw the HBO show Silicon Valley, but Jin Yang manages to make an app for telling you what kind of food your phone is looking at, and it puts out two categories. It puts out the category of hot dog, or anything else, it comes up as not hot dog. The people on the show were a little disappointed. Those were the only two things it could do. So that's just an example of this kind of decision making. I want to say something about noise. Noise is going to be a theme that is going to come throughout this talk, okay? And right here, look, the very first one, I'm going to read it to you. It says, noise makes it hard to detect stuff. Do you notice that? You notice how the words themselves are a little hard to read on that background? That's not a mistake. I did that deliberately. Okay, I'm a little sneaky that way sometimes, right? So noise can make it hard to detect stuff. This kind of brings up the question in our own life. What kind of noise is in your life, my life? What kind of noise is covering up the signal that we might be interested in, or maybe that God is trying to say to us? Yeah? And then noise is actually going to appear not just in this first talk on detectors and classification, it's also going to appear when we're talking about generative models and generative systems. So yesterday, I'm on Twitter a lot, and most of you probably don't know who Andre Karpathy is. He is a kind of a Mozart among machine learning researchers and engineers. He's a guy that even as a graduate student at Stanford, he was doing the most amazing stuff and always really good, and he's been employed at OpenAI and various things. When Karpathy says something, we all pay attention because he's really good at what he does. And he just mentioned yesterday, he says, I'm coming back from a 2-week detox from the internet. And he says, the main takeaway is that I didn't realize how unsettled the mind can get when overstimulating on problems and information. You don't do that, do you? I don't. Joy, do you ever do that? I don't know. I can't relate to that. Yeah, and he says about 2 weeks is enough to settle a lot into a more Zen state. Okay, those of us who are familiar with Christian traditions, right? The idea of going away on a retreat, the monastic life of being away from the cares and worries of the world so you can focus. We understand this, and this machine learning researcher is discovering the same kind of thing. He says, I'm struck by how an overstimulated brain automatically keeps bubbling up problems in the consciousness, creating a state of persistent anxiety and nervousness. After some time in the settled state, this activity just stops. You can sit down and your brain doesn't immediately go into some kind of problem-solving overdrive. Oh my gosh, I relate to that so much. It just stays silent, nothing happens. This is just yesterday. I had to put this in there. And so from the standpoint of noise, this is removing ourselves. One of the things we teach in acoustics, I teach acoustics, when we're talking about isolation, like making a recording studio, one of the things you can do, in addition to making really thick walls and whatnot, is just move your studio out into the country. And that works pretty well. So I had to throw that in because it was, again, so good. Yeah, resonance and damping. This is one of my central metaphors that my brain often goes to. These are graphs from my acoustics class. I teach physics for audio engineering, and a lot of things involved in audio engineering are about music, and things that are making sounds are things that are oscillating, right? And when anything is oscillating, sometimes it has its own natural frequency that it wants to oscillate, and then you may be driving it with some other frequency. The other thing that happens in real life is what we call damping or dissipation. When we have friction, for example, or something that's going to cause the energy in that system to decrease over time. And one of the things that we notice, something called a resonance curve. What I've got here on the left is a schematic. On the horizontal axis, we've got the frequency of the driving force. So something's driving. You could imagine this as being, let's say, all the possible frequencies of, let's say, the radio spectrum. Let's say we're doing FM radio. So all the different frequencies are there, and then maybe you've got your radio and you want to tune to a particular frequency of whatever station it is that you want to hear, right? And so what you do then is you make a resonant circuit, a circuit that will amplify one frequency and it will damp out other frequencies. And the amount of damping that's in the system, so on the one hand, the amount of damping on the right-hand side is how quickly, if we're looking at time going this way and this thing is oscillating, the amount of damping is related to how quickly things die out. But in the frequency domain for resonance, what we find is when you add more damping, your resonance peak, your sharpness decreases. The sensitivity decreases. You're more likely to respond to more, it widens actually, so you're more likely to respond to more frequencies, but you're less likely to respond strongly to one frequency. And we could go into great detail on this, but for me, I see huge metaphors with this in my own life, and I'm going to make those explicit for those who don't immediately go there. I already mentioned something with less damping, we call it a higher quality factor. It's more finely tuned, it's more sensitive. That's like the black line here, okay? When you get to the right frequency, boom, there's this big jump. With more damping, the system's less responsive. And you can actually get to the point where there's so much damping when that little hump goes away completely. There is a finite value, it's not infinite, there's a finite value at which point the resonance peak goes away, and the damping means the system doesn't even notice something that might be going on, so to speak. And boy, there are a lot of places, there's a part where Jesus is talking to people and he's saying, do you not get it? Are your hearts so dull? And for me, when I see that, I think of this red line. I think of the dullness of a resonator that is not able to respond enough because it's so weighed down with dissipation. And this word dissipation appears in a few places in the Bible. Here, I'll say one little thing. In Paul saying, their minds were made dull, for to this day, he's talking about the traditional people in power in the Jewish nation. Their minds were made dull, for to this day the same veil remains when the old covenant is read, it has not been removed because only in Christ is it taken away. Now, whenever we're talking, a speaker is usually cognizant of other experts who are in the room. There probably are some Greek and Hebrew experts who are thinking to themselves, well, yeah, but that dull there, that doesn't really mean a physical shape. That's more like foolhardiness of mine. Yeah, fine, okay. I'm still describing my analogies for what's useful for me and how I think. And I think of this dullness in terms of a lack of responsiveness in the system. And then I think this is definitely very true, though, right? Jesus is saying, Luke, be careful, or your hearts will be weighed down with dissipation, drunkenness, and the anxieties of life. We could call that noise. And that day will close on you unexpectedly like a trap, for it will come upon all those who live on the face of the whole earth. So he's saying, look, if there's a lot of dissipation, you won't notice. The day will come upon you, it'll happen, you won't be ready for it. So for me, when I'm thinking about, am I sensitive to the voice of God? Yeah, where is my sensitivity? Where is my dissipation? Am I finely tuned or not? And we're going to do some more physics analogies to drive that home. For example, right now, there's all manner of radio waves going through us all the time. And are we picking them up? Probably not, because we don't tend to have resonant circuits in us. But we may have a device, and like I teach an electronics class, we can build radio systems, and depending on the amount of resistance or dissipation in the circuit, you may be able to pick up the signal or not. And then that assumes you're actually even tuned to the right frequency. So yeah, how well are our detectors tuned? What's the noise background like? Is there a lot of noise making it hard to distinguish the signal? And are we even looking in the right band of signals? And for that, I'm going to tell you a bit about gravity waves. A while ago, I got my PhD at the end of the 90s in 2000, and we were all getting paid by NSF to simulate gravity waves from binary black hole emergers. And so the idea was a new way of doing astronomy. So when people look up at the sky, or when scientists look up at the sky, there are all these different kind of frequency bands or different types of signals that we'll use to try and notice what's going on. And a lot of these may be electromagnetic in nature. So we've got, for example, the visible spectrum. And you can see some stuff in the visible spectrum, but there's a lot more science going on in other wavelengths. So for example, infrared, you end up seeing something different. So Kobe was a cosmic background explorer. It was looking at a particular range of infrared, where essentially it's showing you the structure of a very early time in the universe. Gamma rays do this whole other thing. When we started doing gamma ray astronomy, we started noticing all these weird, unexpected gamma ray bursts going on. Oh, yeah, in fact, here's a map of the gamma ray bursts, right? And so the question is, if we can look at gravity waves, and we do nowadays, what other kinds of things can we see or can we notice? And in particular, it's really useful for astronomy when you can have a multi-signal system, when maybe you see something happening in the radio and you'll also see something happening in the visible, and you can correlate those things. And eventually they started to be able to correlate gamma ray bursts with other things happening. And we can also detect, for example, neutrinos. We have neutrino detectors throughout the world, and sometimes we're going to talk about music in a little bit as well, and that's going to be really relevant. Gravity waves, I don't want to go into a lot of detail because I think that would sidetrack us, but they're essentially kind of ripples in the fabric of space-time. They cause they cause things to squish a little bit and stretch a little bit, and you can detect it if you build a very sensitive detector, which I'll show you a picture of on the next slide. This was a talk I gave at Belmont. Hearing the still, small voice. These gravity wave signals are super duper duper weak. And then there's a lot of other noise. And it ends up being like putting a microphone on the universe. It's not an acoustical wave, but it's very, very similar. It's like holding up a mic and trying to find out, hey, what song is this? Shazam. So I call it Shazam for space. And we could go into Shazam, a very interesting piece of technology. But this idea, if you have a template of what you think it might be and you try to match that up. And by the way, the early gravity wave detectors were musical in nature, in a sense. They were resonant. There's a picture of Joseph Weber from the University of Maryland back in the day, back in the 60s. And he's got this big old metal bar, which is like a science xylophone bar. It's designed to resonate at one particular frequency very strongly. It's got this super duper high resonance peak, and he tuned it to the one frequency where he thought gravity waves would be most likely to be occurring. And then he covered it. What he's attaching on there are piezoelectric transducers. The same piezoelectric transducer, if anybody plays guitar, like an acoustic guitar, and you want to amplify it, or pretty much any acoustic instrument, when we amplify them, we usually use these little piezo crystals which respond to flexing or compression by generating a little current. And so this is a musical resonant detector, and the idea is with a very strong reaction to one frequency, maybe we can pick up gravity waves. Didn't work. But instead they said, all right, we need to go bigger. And so in middle of nowhere, Washington, okay, no offense, but it really is. That's why they designed it that way. Hanford, Washington, a place where they used to make, they probably still make some uranium and plutonium and stuff. And in the swamps of Louisiana, and there are a couple other detectors throughout the world, they made these big long tubes, and you can see one tube going off in the distance for the Hanford and down below, and there's another tube at a right angle for each of those, and they're 4 kilometers long. And the idea is they're trying to measure little changes in the length of the tube using lasers. And the change in length that they're trying to detect over 4 kilometers is less than the diameter of an atomic nucleus. So they're looking for a change of less than 10 to the minus 15 meters over 4 kilometers. That is a strength to strain ratio of 10 to the minus 21. So imagine 1, 0, 0, 0, 0, 0, a whole bunch of zeros, 21 zeros, and then that last zero you're switching between a 0 and a 1, and you're trying to detect. That is the signal from space, and this was the largest NSF-funded project, period, more than Fermilab for quite a while, right? And one of the things they had to deal with a lot was noise. There's just noise everywhere. And this is just a graph. We're not going to go into the details. But every single one of these lines, well, all the colored lines, are some kind of noise. So they've got quantum noise. Seismic noise, like trucks driving by nearby, could throw off the detector very easily. It turns out that just the tidal variations of the Earth due to the moon are measured by this thing, but not just the moon. This detector can actually detect tidal variations when a satellite goes over it. And they were starting to detect satellites that they weren't supposed to know about. Right? Satellites that weren't on the list were appearing in the detector, right? This is so incredibly sensitive. And then they've got all these different kinds of things, and they add all these up, and that gives you this black line. Now this is the advanced LIGO thing, which came online a little while ago. So it's no longer 10 to the minus 21, now we're down to 10 to the minus 23, and even a little 10 to the minus 24. And the idea with that is we can hopefully see more events and see farther out into the universe. We can detect weaker signals. I say we. I got out of that game a while ago, so my friends still do some of that. But one of the things that we would do then is we would generate these, and I say we because I would do this, we would generate down here on the bottom waveforms. And the idea was this is what we're looking for. And we'd make some kind of template and we'd perform pattern matching between the signal that was coming in and the signals that we had in our library. It really was like Shazam, where Shazam has a library of all the different songs and tries to match what's coming in. And so, yeah, these are supposed to be like two binary black holes. I'm not really sure what's going on with the ring shape, to be honest. I grabbed this pretty quickly. I have other pictures I could have used. But the black holes, they spin around each other, and while they're spinning around, they're orbiting each other, it starts to wiggle a little more, and eventually they start to merge. And when they merge, there's this big old blip that happens, and that's the part that you need the supercomputers for. So pretty much me and tons of people that I knew, we were all doing this little orange part for a while, because this part you can get with some ordinary math, and this other part you can get some ordinary math. But this is what the basic signal looks like. It sounds like, and that's it. And then it's over. And that's what got detected. What's over here on the left, this is one of their resonant systems for filtering. And so the mirrors that are bouncing the lasers back and forth, they're made out of sapphire. They're really nice. And they're attached to a test mass down here. And then they're attached to another mass that's hanging. That's attached to another mass that's hanging. This is attached to another mass that's hanging. Each one of these things functions like a pendulum. And you know how a pendulum has a natural frequency that it likes to swing at? That makes it a filter. So really high frequency oscillations don't really make the pendulum swing any differently. And really low frequencies are low enough that, yeah, maybe the pendulum kind of moves all at once, but it doesn't really swing. And each of these, this is essentially 5 different pendula, a pendulum hanging from a pendulum, and at each stage you get a resonant filter, and they set it so that the frequencies of those filters are all at different frequencies. So essentially it just kills the noise. Any noise that's coming in is unable to make the whole thing resonate. So the LIGO people won the Nobel Prize in 2016, and it was announced, yes, we have actually detected gravity waves, and here's where they are. So gravity waves are real, and we can use them, and we are using them to understand things about space. And that was, 2016, so we're farther along now. If you've got this thing of what you're looking for, essentially what happens with the LIGO system is they apply a lot of filters, and it's what we do in audio engineering. I was telling my audio engineering students the music business is not a good way to make a stable living. Why don't you go work for the LIGO people, and they're essentially using audio type science versions of the audio digital workstations that my students use for music production, Pro Tools and Logic and that kind of stuff. They've got their own science versions of those for LIGO that have different math in them. This is an example of learned filters. And one of the things that happens with neural networks all the time, or any kind of computer vision system. It's loosely based on the human eye, and the human eye has these little receptors that can detect different things, and they learn to detect different kinds of lines often, and then we combine those. So what I've got here is a little, actually this is not the demo, I'll do the demo in just a second. This is just a test image that's got some shapes and things. It's got a horizontal line and a vertical line, a couple diagonal lines, a circle, and some patterns. And then this little guy here is what we call our filter kernel. And what it's going to do is between the input and the output, right now it's set for kind of diagonalness. And so anything that's diagonal is going to make it through this filter and then be presented to other parts of the network farther down. Anything that's not a diagonal line simply doesn't get noticed, doesn't propagate. It's as if it's not there. Let me show you an example of this. This is for a book that I still haven't finished in a long time. It's a book on classification down through the ages. And yeah, so let's do, it's interactive. It's an interactive book. So now I've set this thing for vertical lines. And so what it's going to do is it's going to allow anything in the input image that looks like the kernel that correlates with this kernel image to pass through. So now that's vertical, we've got our vertical line. Notice the horizontal line's not there. And the diagonal lines are there a little bit, but not totally. And similarly, we can turn this off and say, oh, now let's let the horizontal stuff come through. And so now we've got that horizontal line coming. And then it's funny, these different patterns, they kind of change. Some of them make it through and not. I don't want to talk about the patterns, I just threw them in there because I think they're interesting. But mainly if we look at the horizontal and the vertical, and notice that right now that it's set to a horizontal detector, we get the top and the bottom of the circle, but we don't get the sides, right? And just one other little thing. So what's happening in neural networks and computer vision systems is the system is learning a whole bunch of little filters that are sensitive to different orientations, and then those can get combined with other things. This is based on the visual cortex of the cat. And those of you who've taken neuroscience classes, there's some work by Hubel and Wiesel back in, I guess it was the 50s, where they hooked up electrodes to a cat's brain, and they noticed that they hooked up the neurons to an amplifier, they hooked up the amplifier to a speaker, and they noticed that when they passed certain types of lines, like diagonal lines or vertical lines or horizontal lines, the speaker would make a little noise. It would be like, "Rrr." And that was indicating the neuron was detecting something. And we found that different neurons are sensitive to different things. Well, a little bit later, Blakemore and Cooper did this thing, which is, it's all in the name of science, okay? So they would raise these cats, and there's a great video, I don't have time to show you the video, but they would raise these kittens in complete darkness, and then for a little while each day, they would take the kitten out, and they would put it, so I know I got text on top of the image, but we're gonna work with this, right? So there's a little picture of the kitten, and it's got a little thing around its neck so they can't really see itself. And they would stick it in this tiny little kind of mini room that's got, in this example, it's got only vertical lines in it. And then they'd let it do its thing in there for a little while. They'd take it back to complete darkness. And they would do this for a while. And what they found was that kitten's eyes never developed the ability to see horizontal lines. It could only detect vertical lines. And so there are videos, and yeah, maybe I should have included the video, of the kitten, and they got this little stick, and they got the stick horizontally, and they're like, hey, play with the stick, play with the stick. And the kitten's just looking around like nothing. Then they turn the stick vertical, and the kitten starts going for the stick like crazy. And then when they're picking up the kitten, they'll put it on a tabletop. Normally, a cat or a kitten will reach out towards the tabletop as you're doing that. Kitten doesn't even see the tabletop. Like, it sees it, but it doesn't perceive the tabletop. And they did the same thing. They switched the horizontal lines to vertical lines, and they found, yeah, same thing. Kitten raised with only horizontal lines occasionally never develops the photoreceptors for seeing things vertically. And this is really interesting for us as human beings. People who study developmental psychology will say there's a certain window during which certain kinds of neural connections can be formed, and after that, they don't really do that. And the same thing would happen with these kittens. They would grow up, and even if you started taking them back out, like after about, I'm going to guess, 8 weeks, my colleague Carol Sherling, who's a neuroscientist, could help me out on this, but let's guess 8 weeks after that, the window closes on the ability to learn those sort of things. So you can have a completely normal cat who's able to go around the world and do things, but those certain kinds of photoreceptors aren't there, and the cat never develops the ability to learn, even later in life. There's this little window. So think about that for some of the things that might happen to us when we're younger. We learn certain things or we don't learn certain things. It's really hard. And I believe it's through the grace of God that we're able to overcome some of those things that we get. One of the other things that I do a lot in life is signal correlations. And I realize I don't want to lose too many people here. It's going to get fun in just a second, but for me, this is really helpful. This is going back to, this is the signal version of the image thing we just did. And so what this is about is essentially, let's say I've got a sine wave. This little thing means it's sensitive to everything. Check this out. One of the things that happens
Yeah, we get this really big, when our input signal looks a lot like the template that we're comparing it to, or the filter, we get a really big output. And I measured that also here with this green line. And one of the things that can happen with our noisy sine wave, for example, we might get all this extra noise, but we've essentially filtered that out. So the output signal's down here in red. The point here is that the output is this filter is gonna grab the part of the input that matches this thing. And the amount of the matching, the similarity, is given by this little number here called R. Do you ever use R in statistics, the Pearson correlation coefficient? Yeah, it is essentially the cross-correlation coefficient. We use that in astronomy. So many different things. Okay, the mathematicians are like, wait, but you have to remember to subtract the mean. Yes, indeed, you do. But it really is, it's the same thing. It's a measure of similarity between two things. When you're doing an R coefficient for plotting say you're doing linear regression, you're plotting the comparison against a line. In this case, we're plotting a comparison against a sine wave. And here's another fun thing. Let's say I have a bunch of harmonics in this signal. So I've got like the fundamental, and then the octave and fifth, and okay, I'm not going to sing all those. But this little filter, it's going to pick out the one that we want. And notice our correlation's gone down a little bit. And oh, look at this. We got low pass filter. Oh, let's do high pass filter. High pass filter means we're going to try and grab the higher frequency sorts of things. So different filters will allow different sorts of signals to go from input to output. That's my only point. And for us as human beings, our filters, we tend to learn those through experience or in some cases through the blessing of God. And these are essentially based on correlations. Now, correlations are fun, but sometimes we might see correlations where they don't exist. So there's this great website called spuriouscorrelations.com. Yeah, some of you have seen this. Great. I just picked one example, but they'll plot all kinds of different things over the years, and they'll rank them by the R value, by the correlation coefficient. And you've all heard the saying, correlation doesn't imply causality. But a lot of times we tend to do that. We tend to look at correlations and assume a causality. And the point of this website is, that's not always good. So this is number of people who drowned by falling into a pool over time versus films Nicolas Cage has appeared in, right? And so apparently Nicolas Cage is killing people through pool deaths. And there's so many other great ones, and you can even explore your own. He's got an interface where you can choose different categories and see what correlates, like annual sales or annual consumption of cheese and some other totally weird random thing. A lot of them do involve death, though. Just warning you on that. But yeah, correlations they are measures of similarity. They're not necessarily implying causality. So this can get us into trouble. I've talked a little bit about the ears. I want to say a little more about the eyes. So the eye is both, we're going to say, the feature selector. Features are the things that we use to make up a signal, and the detector. Here's an example. This is from computer vision and neural network system. We mentioned that the different neurons can learn different things. And so if we look inside a computer vision face detector, we tend to have these different layers of neurons, artificial neurons, but they're patterned after the visual cortex of a cat and humans as well, right? And what we notice is the neurons that are closest to the input, they learn little bits of lines, like horizontal, vertical lines, okay? And then combinations of those neurons feed into other neurons, and those neurons end up assembling like little parts of eyes or little parts of noses. You can see like an eye, like right there, right? We've got an eye and an eyebrow there, we got a nose there, right? We still don't have a complete face. But then those neurons sum together, and that's what gives us our faces. And so these are from some data set. But if you're having something where you're doing like a facial recognition system, where you're like having people show their face, I don't know, maybe at an airport, for example, this is the kind of stuff that's going to exist inside that system. If you can't, let's say you can't detect horizontal lines very well, then you're probably not going to get any eyebrows in there in later stages of the system, like this guy. All right. The other thing we can ask is, what is the system really sensitive to? The word that gets thrown around in machine learning circles for this is saliency. So when we've got some kind of input, what is the network really keying in on? It's not always the same thing as what humans do. This is something I'm really interested in, is how are what machine learning systems, how is what they do similar to and different from the way humans do things. Might get the same job done, might accomplish the same task, but might do it a very different way, and might even figure out ways to cheat. And here's an example of a model that's learned to cheat in a way. This is a very famous example, although I made these pictures myself using a network I trained myself. There's a data set called ImageNet, which is a benchmark for training any kind of computer vision system. And they have all these different categories of animals and airplanes and cars and stuff. And one of the categories is a fish called a tench. And it's been shown over and over again. If you look inside a neural network that is being presented with a tench, what is it really seeing? Where is its attention going? Oh, I'm sorry. I've never made that before in my life, that pun, and maybe I never will again. Here's some pictures of people. I pulled these off of Flickr. These are Creative Commons license. I ran it through the network to say which parts of this image are most important for the network producing a verdict of this is a tench. What you notice is, so these are all highlighted in yellow. Two things to notice. The fish itself is pretty much not even there in the bottom images. You can see a bit of an outline, but the strongest detectors are all about the people holding the tench. We got the eyes, we got the ball cap, we got the fingertips. The fish is pretty much not in there at all. So this network has learned to cheat. Turns out a tench is a trophy fish. And so for a while, the pictures of tenches that you would see were not a tench in the water doing its own thing. On the internet, like if you scrape the internet for pictures of tenches, what you get is a lot of people holding up their tench saying, oh look, I found a tench. And the network learns that, oh yeah, if somebody's holding up a fish, then it's probably a tench. And this goes on even to later today, we'll talk about generative systems. Some of the early generative systems, like the early text to image systems, I would deliberately ask it to make pictures of tenches, and sure enough, it would make pictures of the fish, but there would also be fingertips in the image that was generated. So it's the same kind of bias. All right, here's another fun one that I like. You know how sometimes you're supposed to identify which images have which and what? This is to determine whether you're a human or a computer. I made this up. Select all the squares that have pandas or skip. And so for you and me, we might be like, okay, I guess all of them. And then the system would say, nope, actually some of them are not pandas. Some of them are pictures of gibbons. Gibbon being VA type thing. And we wouldn't see that, right? And it's because the images with the gibbons have been added a particular kind of noise where the network has learned to fool another neural network system. So you can have a generative system that can fool the detector. And we'll talk about what those generative systems are. They're called generative adversarial networks. All right, a couple more slides and then I'm done. You notice I'm jumping from topic to topic. If that's a problem, I'm sorry, but there are a lot of fun and interesting things that happen. Anomaly detection is another kind of a template matching system. And it's something I think we do in our lives as well, whether we're talking about humans or whether we're talking about, hey, is God telling me to go put on an orange jumpsuit and walk around in downtown Minneapolis shouting at people? We might use some kind of pattern matching of what does this match up with, this idea? Does it match up with sort of common notions of scripture or Christian participation throughout the ages? Or maybe is it an anomaly? Is it an outlier? And this gets used automatedly in so many different ways, where we may have some sense of normal activity, whatever normal is, typical activity, typical lawful activity, for example, and that tends to cluster one way. And then all kinds of other things where people are doing something weird, that appears somewhere else if we're mapping it into a space of features. And like I can recall as a teenager traveling around with my friends, driving in the city, and we're a bunch of nerds and we don't do anything bad ever. But somebody's excited about something, we're moving around, we get pulled over by the cop, by a policeman. And he's, I don't know, y'all were just acting squirrely. And so acting squirrely was this policeman's way of doing anomaly detection. And yeah, it turns out that we were just a bunch of geeks who I don't even know what we were excited about. My brother-in-law works in cybersecurity, and our systems here in the United States are getting constantly attacked. I think there were, like, the number of cyber attacks from, say, China and North Korea combined last year, and Russia, was over 1 billion for the year. And for the year doesn't even sound right. It's probably more like in a month or a week or something like that. And so you have to have automated systems to detect these and to filter them out. Something that happens in Nashville, which I found out is catching ticket scalpers, people who buy concert tickets and then try to resell them. And there are some artists, even some country artists. I saw this from a talk by the IT team of a famous country artist who wanted to make sure that his fans were able to buy his tickets. And so they do this kind of thing where they monitor the sales and try to track anomalies. And yeah, certainly detecting anomalies from space, if you watch sci-fi, that shows up quite a bit. Something else that happens when we're detecting, we may update our beliefs. And I'm including this here because it's going to show up when we're doing our generators as well. A lot of the systems that are operating in the AI space are statistical in nature. And they're not always the way human beings do things. There's some similarities and some differences that we've already looked at a couple of those. One of the fun things that's good to talk about a lot is Bayes' rules. And this is a fun science and faith thing. It was invented by a minister, Bayes, and you can read about him. Essentially saying, look, if you have an idea of the probability of something, and you're interested in the probability of something given that something else is true, how do we adjust that new probability? So what this little thing is saying is the probability of X given Y is given by, and then all the way over here, this is the probability of X all by itself times this ratio. So I would describe here a couple of my examples. Some reason I was thinking shark attack, all right? Your probability of being attacked by a shark, just as a person anywhere in the world, may be extremely low. All right, super duper low, and part of that is because most of us don't live anywhere near where sharks are, right? And so if we then were to include, okay, probability of anybody anywhere being attacked by a shark, and then we say, what's the probability of being attacked by a shark given that, let's say, given that you're in the ocean? Okay, it's still gonna be really small, by the way, so don't worry about that. But it is gonna be higher than if we include all the people everywhere that are landlocked, like those of us in the central time zone for the most part, right? And so we might say, okay, let's say X is probability of being attacked by a shark, and Y is maybe being in the water. So essentially what we do is, or being in the ocean, I guess I should say, rivers don't count. So we say, all right, your probability of being attacked by a shark, given that you're in the water, is the probability of anybody anywhere being attacked by a shark divided by the probability of being in the ocean, multiplied by, and then we flip these two things. So this is probability of being in the water when you are being attacked by a shark. And spoiler, this number is very close to 1. The probability of being in the water when you are being attacked by a shark is almost 100%. All right? The only other example, maybe if a fisherman has hauled the shark up and out of the water and it's still alive, or the shark jumps onto the boat, right? But this first one, this is very close to 1. This thing down here in the denominator is less than 1, right? Probability of being in the water is less than 1. And so a number less than 1 in the denominator is going to mean that your probability of being attacked by a shark, given that you're in the water, is actually going to be higher than the probability of just being attacked by a shark, given that you're anywhere in the world at any time. And that's kind of what we would expect. So this is how this Bayes thing works, and we automate this in our machine learning systems. Now, humans do some similar things. It's just not exactly the same thing, and there can be some differences. And I thought about mentioning I flew over here on a plane, and we could say, probability of dying in a plane crash. I don't want to go into that. It's still very small. But for example, probability of dying in a plane crash, up here, this would be like, given that you're in a plane, right? If you are experiencing a plane crash, there's a very high probability that you are actually in a plane. So that's how some of these things work. Now, on the automated side, spam detectors. This is a very common thing, like those of us who teach machine learning, one of the earliest homework problems we do is make an email spam detector. And using this kind of Bayes stuff, you can essentially, based on the probability of certain words occurring together. Now, over the years, spam makers have made it a lot harder. Those of us at universities, they make these really convincing things where they tell you, I'm your dean and I need some help, can you click this? But in the early days, if you see a bunch of words that are together, like Nigerian prince and Viagra and a few other things like that, if they're all coming together, the probability of those all being in an email that's not spam is very low. Like the number of emails that you get from a normal person that's using all those words together is exceedingly small. And so just by getting a bunch, so you can do what we call supervised learning. You grab a bunch of examples of spam emails, you grab a bunch of examples of normal emails, and you run the statistics on word correlations between them. And you can very easily, through updating, what is prior is this little guy right here, your prior belief. So we update your prior belief, and now we get what's called our posterior distribution. Our spam detectors are very good at this kind of thing. Now, a lot of people in the more materialistic, naturalistic side of things will say, this is what all of us do. The human brain is just doing Bayesian probability. And there's a whole sort of cult of Bayesianism. And if you go to Cambridge, you will meet those people. In particular, they do a lot of great science, but I don't necessarily agree that the philosophy needs to go as far as they want to take it in some cases. But this is I'm mentioning this here partly because it's for our detectors, like spam detectors or other kinds of detectors. But we're also going to see this kind of stuff after lunch when we're talking about our generators. So I'm setting us up for that a little bit later. Okay, so I thought that at this point in the talk I might be out of time, and I figured, you know what? There are all kinds of really interesting examples of detection in medicine. Just really simply, we lived through the COVID time. And so detecting, do you have COVID or not? Any given test is going to have some false positive rate and false negative rate. False positive rate being it tells you have COVID when you really don't, or it doesn't detect COVID when you really do. And then multiply those probabilities by however many millions of people are being tested, and there will be some mistakes that happen. And the efficacy of a test is essentially measured based on some combination in a formula of our false positive and false negative rates. But these happen everywhere. We use them in machine learning, in computer vision. We use them in music. There's this whole field that I'm a little involved in called music information retrieval. And Shazam is an example of that. Detecting cover songs, detecting people taking a song and re-uploading it somewhere else. We look into that to try and make sure that we can get our musicians paid. And I've been involved in some really interesting things involved in trying to track things to make sure musicians get paid, and we can go into that if we want. One of the other things that we wonder sometimes is, how confident are we in our detection? Like we said, okay, we think that this is this or that, but do we really have some idea? Can we give a probability, or can we give an estimation of the confidence interval? And a lot of times in science, the way we do that is we take a bunch of data points, we plot some kind of distribution, and then we look at the standard deviation of our distribution. We break this down into confidence intervals. And a lot of times in science, we might say in order to report a result, we want to be at least 90% confident or 95% confident that this is true. For the LIGO stuff, since it was such an important thing, I don't even know how high the confidence interval was before they were willing to report it because they were so worried about a false detection. One of the things that we do in machine learning when we're measuring our confidence intervals is we plot these things called rock curves. It's called the area under the curve of the receiver operational characteristic. I know, that's a mouthful, right? But it goes back to the days of planes and radar. And so this is my picture. So radar was invented by the British around the time of World War II. And you might detect that there's some kind of plane out there. Actually, you don't even know it's a plane yet. There's something up there. It's over there. What is it? And is it friend or foe? Is this like some British plane group that's coming back? Or is it a new German attack group? Our response to those two things are going to be a little different. We don't want to call out the anti-air defenses on our own planes coming back in. What they would do for any kind of detector of any kind, you can plot how things are doing. I mentioned our false positive rate and our true positive rate. So true positive rate is where you say, for example, with COVID, the test says you have COVID and you actually had COVID. And the false positive rate would be, it says you have COVID, but you really don't. And so what they do is they plot these two things on curves. And so the rate is measured in terms of percentages, and we tend to write percentages between 0 and 1 in science, right? So we got this graph. A totally random classifier is this diagonal line in red, which is saying if it's totally random, then it's going to give a false detection or a true detection 50% of the time. If you can get your true positive rate above your false positive rate, another way to think of this false positive rate is it is a line of slope 1. And so the random classifier, the false positive rate, and the true positive rate at every point are the same. you want something with more true positives than false positives. You want something that's in the upper diagonal here. A perfect classifier is this little guy, this little dot, which says that the true positive rate is 1 and the false positive rate is 0. What we do with our detectors is we vary our parameters and we watch how these curves change. And so when we first start out our system before we're training, and so think we're trying to train a system to detect, to distinguish good from evil, to bring it back a little bit to the Christian morality a little bit. And in the beginning, maybe as a child, it can't distinguish it, he, she, can't distinguish good from evil. But over training, the system, the person, gets better and better at it. Maybe not perfect, but essentially you end up with this point where you are somewhere between false positive and true positive. So this is a family of, I'm going to go back to machine learning for a second. This is a family of models. So any individual model is going to be a point on one of these curves. So it might be like that spot right there. So we know this is the false positive rate. Maybe the false positive rate is 0.4 and the true positive rate is 0.8, right? Notice they also tend to add to 1, which is nice, right? And then one of the things we do is we say, all right, how can we change the system to maybe make that better? And so by plotting these kinds of things and varying things, we can see this curve. So receiver operational characteristic is the name for this kind of curve, and it applies to whether we're talking about planes or COVID detection and one of the things that got me started on writing the classification book and teaching the honors class was when Dr. Doan and I are at Oxford, and I was thinking about machine learning all the time, and I thought, everybody around the room, the theologians, the philosophers, the English professors, those kinds of folks, they're debating all these sort of moral and aesthetic questions. Is this good? Is this bad? Is this art? Is it ugly? Even, is it science or is it religion? These sorts of things. I thought, wow, from a machine learning perspective, these are all classification problems, and we're classifying. And really, there are enough people in Silicon Valley that just try to build systems to do things, whether it's a good idea or not. I say, what if people are, this would be a bad idea, but what if somebody tries to make a machine that will try to make moral decisions? Is this good or is this bad? I thought, oh, obviously that's silly. No one would ever do that. But somebody probably would, right? Someone in Silicon Valley is probably building whatever stupid idea you can think of. Someone's trying to build it and they're pitching it to investors, right? But I thought, okay, this moral thing. Well, yeah, sure enough, within a year or two, the Allen Institute for AI in Seattle released their Delphi, the Oracle system, where you can ask it moral questions. Like, is this good or is this bad? Hey, I'm thinking of moving my boundary line on my neighbor, and is this good or is it bad? And it'll give you an answer based on this. And a lot of these systems were trained on just, in some cases, the internet. For example, there's a Reddit thread called AITA. Am I the bad person? A is I won't say it in our present company, but am I the bad person in this situation? And they're asking the crowd for a moral delivery on my girlfriend was doing this or this, and I said this, and now she won't talk to me, but I thought I was in the right, and so everybody tell me, am I the bad person in this situation? And people would scrape this, and then they would train a classifier based on yes or no, and then, yeah, you could ask these little questions. Hey, how's this going? And this sounds like a don't do that, but people did it all the time. And so same kind of thing happens here. And you might say, that doesn't matter, that doesn't have any real consequences, but it does. For example, those of us, we live our lives online in many cases. Automated content moderation happens all the time, where maybe it's detecting, for example, let's say hate speech, right? Hate speech detection. Now, hate speech is bad, right? But saying that somebody who's not committing hate speech, having a false positive on that, means that somebody's tweet or post or whatever is getting censored. And I know there are a number of Christian groups that were reporting this kind of censorship over different things for different reasons. And so this kind of classification stuff and this accuracy applies to a lot of our lives. Yeah. So, we have time for questions for discussion. How are we doing this?
We have time for like maybe 1 or 2 questions.
I don't know a lot about LIGO, but one thing that struck me when you were talking is they had theories, Einstein's theories of how the black hole gravity wave should work, if I'm understanding it right.
Yep.
And then those were the filters that they used for all this noisy stuff that LIGO's got. So then they said, oh, we found it, we're sure we found it. Einstein's theories are proved. I was just thinking as you talked, well, isn't that all we were looking for? We were looking for, so there could be a lot more out there in gravity waves. We just found the ones that were supportive of Einstein's theories.
This was a bare minimum. One of the generic predictions of Einstein's theory of relativity is that gravity waves would exist. And previously in the 1980s, indirect evidence of gravitational waves was found in the way that there's a little bit of wind going, and you can see like leaves moving and branches being blown by the wind, but you can't see the wind. And so similarly, people found there's a binary pulsar out there, and they found that the motion of this binary pulsar was exactly consistent with the presence of gravity waves being generated by the system. So pretty much, the theory said gravity waves need to be there. The pulsar observations say gravity waves are happening, but we hadn't detected them, hadn't actually detected them directly. So this Nobel Prize was for direct detection of gravity waves. However, the hope there after that was, okay, now that we can detect gravity waves, can we use them for astronomy? Can we learn other things about the universe based on gravity waves? Now, it is also true there are other theories of gravity that deviate from Einstein's theory at very strong gravitational fields. However, so far, like the very strong gravitational fields occurred during that little merger blip of the gravitational, the binary black hole merger. And so far, nobody's detected any deviations. So it is still possible that, yeah, maybe Einstein's theory is not complete. Maybe there are other things that happen. We believe that there's some sort of quantum gravity thing that will take over at even higher signal strengths. But yeah, right now the data's out. And since Einstein's theory is kind of the simplest one of these other variations, we're still just going with what we got on that. Good question. Okay, I think that's it. So we're gonna now move on to other things. Thank you very much.